Hello, so today we are going to do this Leetcode problem. It's part of Leetcode April Daily Challenge, recover binary search tree. So the problem says we get a root of a binary search tree where exactly only two nodes of the tree were swapped by mistake, and we want to recover the tree so that it respects binary search tree properties. Basically, the left side should be smaller than the node and the right side should be bigger. So we need to recover it without changing its structure. So we get two examples here. 1, 3, 2. So this node 3 here is bigger than 1, although it's in the left side, but it's in the left side. So left side should always be bigger than the node or the root, and then the right side should be left side should be smaller than the node, and the right child should be bigger. And this is violated here. And so when we swap them, we get the properties that we want, which is left side smaller, right side bigger. If we take a look at the second example here, here you can see 2 is to the right of 3, but it's smaller than it. So these two are out of order. So you can see it's not always just the direct child and the parent. Here, for example, 4 is good because 2 is smaller than 4, but 3 is not. 2 is a right child of 3, but it's smaller. Okay, and so if we swap the 2, we get a valid binary search tree where the node always has its left child smaller than it and its right children bigger than it. So that's the problem. Now, how can we solve it? Well, the simplest solution, right, is to do in-order traversal, and that will give us a sorted array, and then we can just check in that array. We can get a sorted version of that array and just replace all the node values with the sorted version. So yeah, this one is like expensive because it's over-ligand solution. We need to sort the values, but it's really straightforward. So let's do this straightforward solution first, and then we can go to a more optimal solution. So the first is we will just collect a list of nodes using in-order traversal, and then after that we just sort the values, and then we assign to each node the right sorted value. Okay, so yeah, this one should be quick and really simple to code. So first we'll just do our in order that collects the node in the right order. So usually to collect the values we do something like this in order. Well, we go to the left, go to the right, and then collect values. And to collect values, the simplest way to do it is just to do plus node val. We could have like a property on the class called values and append to it, but it's easier to just do this. So we could do that and then return. If node is null, we reach the end, we can return empty list, so that the concatenation here works. But what we want is to change the value in the node itself, and so to do that I will collect the nodes instead of just the node value. Okay, and so now to get the values, so first let's just have the nodes is in order of node, right? And now to get the sorted values of the nodes, we'll just do sorted on the values, which is node.val for nodes in nodes, right? For node in nodes. So this will give us the values in sorted order. Now we can just go through all the nodes and modify them so that they are in order. Their values are sorted, and that will give us what we want. So to do that, we'll just go through the range of length of sorted values, or of length of nodes, doesn't matter. And now for each node, we want to assign to it the sorted value at I. And so this, we don't bother ourselves with finding exactly where the mistake happened. We just update everything to have the sorted values, and that will give us a BST, because a BST, the in-order traversal, gives us a sorted list. And so we just do that, and that should be it. Okay, so which looks like we have a small issue here. This should be plus here. Yep, here we should pass through it. Okay, it looks like there is a small issue somewhere here. So we got the sorted values, and we got the right in order traversal. We called it. Oh, okay, sorry. Yeah, we shouldn't replace the node itself, we should replace the node value. This is the right way to do it, yeah. Okay, and now if we submit this, it should pass. Okay, so that passes. But this is not ideal, like we are not finding the exact two things that we need, and this is also of lag n and lag n because of sorting. And we have open space. And so how can we improve this? So one way we can do this is, let's just find the mistake in the array of nodes instead of while traversing. That will make this simpler. So how can we do this? Yeah, let's go to the drawing board and see how we can do that. Okay, so let's take two example arrays. Arrays, and you can imagine those arrays are just the node values, right? So if we had, let's say 1, 7, 4, 5, maybe 2, 9, 10, right? So if we take a look at this array, what is the problem? Well, we have here 7 is bigger than 4. This 7 should not be here. 5 is also, 2 is also smaller than 5, so it's messing up the sorted order, so this one should not be here. If we swap these two, we'll get 1, 2, 4, 5, 7, 9, 10. So we'll get a properly sorted array if we just swap these two. The second example is, so this is example 1. If we take a look at the second one, it's, so here the mistake is in non-adjacent values. So and so in that second example, let's take for example maybe 2, 7, 9, something like 30, 10, and then maybe I don't know, maybe 50 here. Okay, so what is the problem here? Well, you can see that it's just here, these two. If we swap these two, these are in order, 2 and 7, 7 and 9, so it's increasing until 30, and then increasing for 10 and 15, but 30 and 10, if we swap these two, we get the order back, the right order. So if we do that, we get 2, 7, 9, 10, 30, 50. So we get the right order. So with the right example, what we need to do is just we need to find the place for the first mistake and the place for the second mistake, right? And here the first mistake is here, and then the second mistake is here. So how can we do that just for an array? So what we can do is just loop through the array, right? And since we want to compare every element with the next, we can just go through the length of the array here, but we'll start from 1 because so that we can check the previous value. And so what we'll do is just check if, let's say this is an array, so we'll check if the value before is bigger, then that means that there is a mistake there. If the value is bigger than array of I, then that means we found the first mistake, right? But since we want, so let's initialize our first mistake to maybe -1. Let's say our array only has positive values, right? So what we want to do in addition to checking the values, we want to check that we haven't assigned yet our first mistake, because otherwise we will assign the first and second mistake place to the same variable, right? So if this is equal to -1, which means it's not assigned yet, and the previous value is bigger than the current value, then we will mark that the first mistake happened at position I. Okay? I-1, sorry. And so in this case, we will find, okay, 7 is bigger than 4. First mistake is at position 7. For the second mistake, it's after we set the first mistake, but we still need the values to be, the previous value is bigger than the second value. Well, what should be the index for the second mistake? So here we have that 5 is bigger than 2, and the mistake is actually at 2. So I-1, I, so the mistake is at position I. We are looking, this is the main idea, is that the first mistake, it's the value where the mistake happens is at I-1. The second mistake, the value where the mistake happened is at position I. And so what this means here is that we can assign second mistake position I. And this is the main idea here, is that the second mistake is at position I, and the first one position I-1, and if we swap those two, we'll get the proper order. And this works also for adjacent values, so we'll find, okay, 30 is bigger than 10. This is I-1, this is I, so we'll assign first mistake to I-1. And then we iterate and we find, okay, for I-1, for 10, we'll find, so 10 is smaller, but 30 is also bigger than 10, but here we would have, sorry, we just need to adjust this a little bit without doing an else, because if we do an else, then we won't assign the second mistake. What we need to do, this is I-1, and this is I, so once we assign it, we'll find, okay, it's also bigger, so we will assign I to the second mistake. So first mistake would be this, second mistake would be this one. This is for the case where they are adjacent. So this is the main idea. Now this is for an array. Now for our case where we have an array of nodes, that we can just get an array of nodes like we did earlier with in order, and then just apply the same thing, except now first mistake will be pointing to a node, and second mistake will be pointing to a node. So yeah, let's do that in code and see how it works. Okay, so let's modify our function that we did earlier to do the same thing that we did for an array in this conceptual explanation here. So we no longer need to sort, but we still need to go through the array of nodes in the same way we did for an array of numbers. We'll start from 1, and now we'll need two things to store the first mistake and the second one. Okay, and since we will put indices there, we can just have -1. Okay, and now we will check if the nodes at position I-1 in the same way that we did for the array, but here to get the value, since it's a node, we need to do that val. If it's bigger, and for our case BST, because we are considering equal to be out of order, we will do bigger or equal. And then for the nodes at position I, that val. Now if this is the case, we need to check if the first mistake is not assigned yet, which means it's equal to -1, then we need to mark the first mistake to I-1, like we said earlier. Otherwise, or not otherwise, but in any case, we want the second mistake to be at position I, right? We are not doing an else, so that we can, for the adjacent, the case where the mistakes are adjacent, we want to set the first one to I-1 and the second one to I, so we can swap both adjacent values. And in the other case where they are separate by some distance, then we will first assign these two, the element and the one next to it, and then in another pass we'll find the second mistake and we'll assign it to I. Okay, so that's the idea here. And now once we know the positions of the mistakes, we can just swap. And so nodes at position first mistake in Python we can do the swap this way, and so we'll just swap these two, right? And so that would be here in the first one is we swap both essentially, and that's pretty much it. So if we run this, okay, it looks like we have a small problem here. So we have the first mistake, second mistake, we go through the list and we check if the values, I think it's just because the indentation is not working properly. Yeah, so actually what we want to change is the values. Right, sorry about that. What we want to swap are the values, because if we swap the nodes, then we'll swap the children as well, and that's not what we want. Okay, so let's run this. And let's submit. And that passes test cases. Okay, so now a slight thing we can do, we don't need to keep track of the indices, we can actually just keep track of the nodes themselves. So we can just change these to be nodes instead. So this would be the node at position I-1, and this would be the node at position I. And now, since it's nodes, we don't need to get them, we can just do the value like this. Hopefully this makes it easier to understand. And with this, so here we need to check if not first mistake, which means basically if it's none. Okay, so that should be good. Let's check. Okay, so that passes. Okay, so this solution actually is oven, because we need this. It's oven time and oven space. We need this nodes array. How can we get rid of the node array then? So I'll do a couple of changes to this here to make it easier to transform to a solution where we don't need an array. So what we are going to do is mark this. So this is the previous value, right? In the traversal, in the in-order traversal, this is prev, and then the current node is this. Right, so this is current and this is prev. And so first mistake we assign the previous value, and the second mistake we assign current. Right, and so now let's just make sure this still works. Okay, looks like still does. Okay, so now you can see what we are doing. This is the in-order traversal, right? But this is where we are processing the node. And so we can just try to put that here while we are doing the traversal. A couple of things we'll need to do. We need first mistake, second mistake, and the previous pointer. But since we are doing this recursive function here, to simplify it for us, we'll just make these properties for the class. So let's just do self.first mistake, self.second mistake, and we'll need self.prev. Okay, and we'll do in order. We no longer will need to collect the list. Let's just comment this. We'll still need to swap in the same way at the end. So let's just keep that, except to reference the new property values. Okay. And now we'll go here. We no longer need to return a list. We just return, and we no longer need a list. Okay, so here we'll process instead of adding. Okay, so we'll need to process the node here. And what we said is that we just need this. This is the processing that we had before. And so let's just replace this with the value. So now what's current? Current is just the current node we are processing. So that's node. And this would be self.prev. And this would be the current node. Okay. So we are doing the exact same thing. When the value is bigger, we want the first mistake, the position at the first mistake to point to the I-1 position, which is the previous value. and the second mistake to point to the node itself, or the I position. And that's exactly what we are doing here. And now we need to update prev, right? Before we were assigning it in the list to the previous value, but here it will be the previous, we'll do the next call, so we need to update the prev. What should it be? It should be just the node, right? The next call will just use the previous value, process it. And then here we need to point to the right variables. So self.first mistake and self.second mistake. And same thing here. And that's pretty much it. We just translated this instead of doing it in the for loop. We are doing it while we are traversing. And now this should be enough. Let's just call in order root now after we initialize the values. Okay, so if we run this, here we need to check to make sure that we have a previous value. And if we use all examples, submit, and this passes test cases. One thing you might think here is that, okay, why isn't too many class variables here? Can we do better? It's harder to do better with the recursive version, but we can do it with the iterative version. And so let's write our in order first in iterative way, and then update it to have this processing that we did here. So we'll comment the recursive version, and we'll write our iterative version. So for the iterative version, in order is pretty straightforward. We have our stack, and then now for these two, we no longer need them to be self, because we are not doing a recursive solution. So let's just put them back like this. And we need our current node to point to root, or our node to point to root. Let's call it current, that's easier. And now while stack or current, okay, basically stack is after we push all the left side, it will have elements, and current while we are to traverse. Initially stack is empty, but current is not. And so here we will go all the way to the far left. So this is just in order in iterative way. And so here we need to append each node, and then here we process, and we do current equal to current.write. So this is the template for in order traversal in an iterative way. Okay, so now we'll just do the same processing we used to do here, except now this needs to be if prev, and we just get rid of all the self values that we had before, and place node with current, because that's what we are calling it now. And this should be it. Yeah, and this should be it pretty much. So this will go all the way to the far left, and then push to the stack, and then we take the topmost left, with the top left element, which in this case would be the leftmost element. Check if it process it. Check if it has a right node. Process that node and its left children, and keep going like that. So pretty much the same in order as the recursive version. And then the processing here is checking if the previous value and the current one are out of order. If they are, detect the first mistake or detect the second mistake. And then at the end, it just swaps. So we no longer need to call our recursive function. And these are no longer self values. They are just properties of the function. So we can remove that. And let's run this. Okay, looks like we have just something with the indentation here. Cool. Okay, so current is going to be equal to current. Oh, sorry. For the processing here in order traversal, we need to pop from the stack, and that will be our current. Because when we exit this while loop, right, current is none and that's why we exited. And so we need to pop to get the leftmost element that we haven't processed yet. And so if you run this, it should work. Let's submit. Okay, and that passes test cases. And this solution is, in terms of time complexity, we do at most the number of elements in the tree, and we are not using extra space, only these 3 variables. Sorry, we are using the extra space for the stack, but we have to for in all the traversal. But we are not using any other extra space. Yeah, I think that's pretty much it. So you can see with the iterative version, it's easier to not have all of these self-dot variables and global variables, essentially. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you in the next one. Bye.